Hey everyone, welcome back to our YouTube channel. In today's video, we'll be seeing the solution for the last question of division 2, that is Beautiful Bracelet. So let's take a look at the problem statement. We are given with X number of bits and correspondingly we are given with the color of an ith bit which is indicated by QIs and the beauty of an ith bit which is indicated by BIs as specified. Also we are given with the color range which are the integer values from 1 till up to R. So we are supposed to choose R different bits from the X bits which are given such that they have distinct colors and we have to make a bracelet out of them. Now to determine the beautifulness of that bracelet which is being made, we'll be using the bitwise XOR operator and we'll be taking the bitwise XOR for the beauty values of the bits which are added to make the bracelet. Now there could be multiple possible ways for making that bracelet. So we have to determine the beautifulness of the kth greatest beautifulness amongst the all possible ways of making the bracelet. So how to do that? Before moving towards the approach, we'll see the input format. So we are given with three integers x, r and y and we have seen what exactly they denote and correspondingly we are given the values of color for each bit and the beauty for each bit. If we take a look at the sample input, so here it specifies that we are given with 4 bits. Now there are two possible values for the color, that is 1 and 2, and it also indicates that we are supposed to choose 2 bits out of the same such that they have distinct colors. Now 3 indicates we have to find the third greatest beautifulness among the all possible ways by which we can make a bracelet out of these 4 bits which are given to us. Now we are given with the color values. Color is here too, and correspondingly the beauty of that particular bit is 4, and similarly the values are specified and the output that we get for this sample input test case is 5. The explanation is given over here. Now let's see how we could solve this particular problem. So the core of the solution to this question is meet in the middle technique. We'll see how that could be implemented and how we could solve this particular problem using that technique. At first, let's take a look at the code. So within the initial part of the code, that is over here, we'll be taking the input values. So as specified, x and r are taken as the input. And accordingly, I'm having a vector of vectors initialized over here. So we'll see why exactly we are using it. As we can see the input format. So we are given with the color values and correspondingly we are having the beauties for those bits. So we'll have these color values for determining the index and correspondingly we'll be storing the beauties for them. So let's assume that we have a vector something like this. Now the index are 0, 1 and 2. Now it's a vector of vectors, so each element will be another vector like this, and correspondingly for the all other elements as well we'll be having vectors over here. Likewise, now what we'll be doing, we'll be having these index values as the color and we'll be storing their corresponding beauties within this particular vector that we have over here. So here we are given with two possible values 1 and 2. So for 1 we'll be storing it at the index 0. So the values are 2 and 3. So 2 and 3 will be stored over here as the beauties of the bits whose color is 1, and correspondingly for the color 2 we'll be storing it at the index 1, that is 2 minus 1, and accordingly 4 and 6 will be stored in this particular vector which is over here. Likewise, we'll be storing the beauties of those vectors in the sub vectors, and the color for the same corresponds to the indices which are over here. So for doing that, again we'll be having y as the input, after which we'll iterate over the possible number of bits that we have, and correspondingly we'll be taking the input for the color values and the beauty values for the same. Now color minus 1 will indicate the index, wherein which we have to store the beauty for that corresponding color. So we are storing the beauty for all the same colors in a certain vector, and this is what it would look like. Now after which we are sorting that particular vector. So the first parameter will be vector dot begin, then vector dot end, that is we'll be sorting the entire vector which is over there. Now it's vector of vectors, so we'll be sorting it in this particular manner. Let's say this is what my vector looks like, and over here we are having another vector of size 3, or let's say of size 2, and here I'm having another vector of size 3, something like this. So the third parameter indicates that we'll be comparing the size of the corresponding vectors as its vector of vectors. So each of the element is a vector itself. So v0 and v1, let's indicate them as the two corresponding vectors within the original vector that is there. So we'll be comparing the size of these two vectors. So the sizes of these two vectors will be compared with them, and accordingly we'll be sorting them in the descending order. So this will come over here and this will come over here. Likewise, this is what we have written over here. That is, it will return true if the size of v0 is greater than that of v1, and accordingly we'll be sorting that particular vector as per the sizes of the inner vectors in descending order. Once we are done with it, then here comes the main algorithm, which is the mid in the middle technique that we'll be using in order to solve this particular question. Now, as given, we have to use the bitwise XOR operator, and we'll be taking the XOR for the beauty values of the bits which are supposed to be there within the bracelet that is to be made. So let's see how this mid in the middle algorithm or technique could be implemented. So for the meet in the middle approach, we'll be having two different subsets, which are disjoint subsets, which are indicated like over here in the form of an array having two elements within it. And each of these elements are nothing but vectors. And again, the data which is being stored within these vectors is of type long. Now, when we are using STL, we generally use the double brackets or the double curly brackets in order to denote the array. So what this mid in the middle approach does is we'll be having two different disjoint subsets, and accordingly we'll be appending the XOR values within these subsets. Now how to do that? It basically tries to have the size for both the subsets nearly equal. This is the reason that it will be comparing the size of these two subsets, and accordingly it will decide in which particular subset we should append the XOR value. Now why we are doing the XOR? Because the question demands the same. It asks us to do the bitwise XOR value for the beauties of the bits. Now let's see how it could be done. So we'll be having this P array, which is having two elements within it, and each of these elements are nothing but vectors as indicated over here. Initially we are storing 0 in both of them, so we'll be iterating over this V array which is over here. So within these V array we are storing the beauties corresponding to the color, and accordingly we have already sorted it. Now what matters to us is not the color but the beauty for the bead. We just need to make sure that the colors which are introduced within the bracelet should be distinct one, which could be done with the help of these approach, that is vector of vector approach. Now while iterating over these particular vector, so when we talk about v of I, then it will ranges from I equals to 0 till up to the size of that particular vector, and here as we could see the size is 3 for this particular example. As the example changes, the size will vary. Now we'll be comparing the size of this p of 0 with p of 1. If the size of p of 0 is greater than p of 1, so obviously this condition will return me true, and we are taking the integer value for the same, so the true will be translated to 1, so the flag will be 1. Then we have an empty vector which is array or arr. Then we'll be iterating over v of i's. So what this v of I indicates, when I equals to 0, it indicates v of 0. So v of 0 indicates this particular value, and accordingly within the sorted vector which is there. So v of I is nothing but indicates these sub vectors which are stored over here as indicated within these diagrams, and accordingly we'll be iterating over these sub vectors one by one, and at the same time we'll be using a nested for loop wherein which we'll be using x as the iterating variable, and we'll be iterating over this p of flag. Now depending upon the condition, the flag value will change. Here if the condition turns out to be true, then the flag value will be 1. If the condition turns out to be false, then in that case the flag value will be 0. So let's consider the initial case. So both of them have size 1 because 0 is stored within them. So the condition turns out to be false because both of them have equal size, and the condition turns out to be false. In that case, the flag will be initialized to 0. So p of 0 will be iterating, that is this particular vector will be iterating in the first half, and accordingly we'll be storing the XOR values for V's, that is the beauties which are stored within this particular vector as indicated over here. So the beauties which are stored within this particular vector will be iterating over them, and accordingly we'll be using X to iterate over P of 0 in the initial iteration, and we'll be taking the XOR value for the same. We'll be using this dummy array in which we'll be pushing those XOR values, and correspondingly we'll simply exchange P of 0 with this ARR, and this thing will happen in loop. That is, we'll repeat this particular thing for all the possible colors that are there, and accordingly after the first iteration the size of P of 0 will be more, so the condition will be turn out to be true. In that case flag will be 1, and in the next iteration we'll be iterating over P of 1, that is the XOR values will be stored within P of 1. So this approach basically tries to balance the sizes for these two vectors that are there, and accordingly the XORs which are stored over here will not be stored over here. We'll be taking the XOR for the remaining elements, and if you'll notice, then as we go on iterating, accordingly new colors will be introduced. So whenever a new bit is introduced, we are iterating over the possible values for the beauty of that particular bit. That is, let's say after 2 we are introduced with a bit having color 1, and there are two such bits, so their beauties is 2 and 3. So we'll be iterating over these two values, that is 2 and 3, and correspondingly we'll be taking the XOR values with the previously stored XOR values within this P of i's, that is P of 0 and P of 1. So it nothing but indicates that we are forming the bracelet. We are taking into consideration different combinations, and this is what is the core for the meet in the middle approach. Now let's move towards how we could develop the answer from the same. So let's initialize the answer variable as 0, after which we'll be having a vector a. Initially we have stored this P of 0 and P of 1 which we obtained from this particular approach, that will be stored as an initial value within a. So this is a vector which consists of an array having two elements within it. So you can see that it is an array having two elements within it, and each of that element within the array is a vector. So P of 0 and P of 1, both of them are vector, and correspondingly the elements within them are of type long. And this is how the structure of A actually looks like. So it's basically an array, or sorry, a vector which is storing the array of size 2. Now we'll be using B as the iterating variable, and we'll have a for loop from B equals to 59 till up to 0. Now the reason for the same will be clarified as we move further. And then we are initializing a dummy array over here, that is ARR, which we are initializing it as a vector. And again, the data being stored within it is an array of size 2. Within this array, we are again having one more sub array, which is of size 2. And we are having a vector within this particular sub array as its elements. So to clarify how this ARR would look like is, basically within this ARR, we'll be storing NAB array, as you can see over here. So we are having this NAB array, which is an array of size 2. So initially it's empty, so it's an array of size 2. So it has two elements within it, as you can see. This is the first element, this is the second element. Now what it specifies is, these two sub elements of it are also the array of size 2. So as you can see, within this particular element, we are having two vectors as indicated. So it's nothing but an array of size 2. It is also an array of size 2 which is being stored within it. And we are storing vectors. So this is one vector, this is the another vector, this is again one more vector, and this is another vector. So these NAB values, when stored within a vector, that vector will be your ARR. Likewise, then we are initializing count as 0. Now what we'll be doing is, we'll be iterating over this A array that or vector that is there, and we are using AB as the iterating variable for the same. So as you can see, A is a vector, so A will be taking all the possible values within the vector. So what the vector is storing, it is storing an array of size 2. So AB is essentially an array of size 2. So initially my AB will be equals to this, which is being highlighted. So when we talk about AB of 0, So AB of 0 is P of 0 and AB of 1 is P of 1. Likewise, then we'll be having an array NAB, which I discussed right now. After which, as you can see that we are initially having only two possible indices, that is either 0 or 1. So we'll be taking a for loop for iterating over these AB values, and accordingly we'll be running it for 0 till up to 1. We'll be using X as the iterating variable to iterate over AB of I. So as discussed, initial value of AB is this, that is an array of size 2. Now AB of I, so initial value of I is 0, so it will indicate AB of 0. So initially AB of 0 is P of 0, AB of 1 is P of 1 as indicated over here. Now what we'll be doing for this particular for loop, we'll be storing the X values within this NAB array which is over here. So how to do that? We'll be having I as the first half to indicate whether to store in the first half of it or whether to store in the next half of NAB, because it consists of two indices. And the next part is an expression. So let's decode this particular expression. We'll be checking this B bit within this X value. Now X values are nothing but, as we know, P of 0 and P of 1 are storing the XOR values as indicated over here. So we are iterating over these XOR values, and accordingly that XOR value for which we'll be checking the B bit. If we simplify this right shift operator, so it nothing but indicates X upon 2 to the power B. Now if we look at the possible values for the beauty within the constraints, so it's 2 to the power 60 as indicated over here. So this constraint actually specifies why we are iterating over this particular bounds, that is from 59 till up to 0. Why we are iterating over this loop is being cleared with this constraint which is specified over here, because the permissible value for BIs is 2 to the power 60. And likewise, if you will see, so it's this particular term which is over here, it will result in X upon 2 to the power B. So your 2 to the power B should not be greater than that of 2 to the power 60. Likewise, and the answer that we'll get for the same will take the AND operation with 1. So what this signifies is we actually want to check the B bit within this XOR value, whether that bit is set, whether that bit is equals to 1 or not. So when we right shift it, we'll be taking AND operation with 1. So accordingly, we'll get 0 if this particular bit is 0, and we'll get 1 if this particular bit is 1, which indicates that the value for the B bit in this X, if it's 0, then we'll get 0 as this particular expression's evaluation, else we'll get 1 as the answer. So correspondingly, we'll be storing these XOR values within these sets which are over here. Now, to simplify up things, how exactly it's getting stored is P of initial value of I is 0. So NAB of 0, then we'll be checking this particular condition. So assume that the B bit is equals to 1. It means that this AND operation will result into 1. So all of these XOR values which are having their B bit equals to 1 will be stored in NAB of 0, 1, NAB of 0, 1. Now these are the XOR values within P of 0. That's the reason they are getting stored in NAB of 0, 1. If it's P of 1 or this next half, then as it indicated over here, it will be AB of 1. Correspondingly, we'll be storing in NAB of 1. This is your NAB of 1. And within this NAB of 1, we have to decide whether to store it over here or to store it over here. So this will be indicated by this particular expression. Again, let's assume that the B bit within this XOR value is, let's say, 0. In that case, this will be NAB of 1, 0. So likewise, we'll be storing in 1 of 0. So here that XOR value will be stored, else it will be stored in the next half of the same. So what we are doing, we are simply having those XOR values, and depending upon the value for the B bit, we are segregating them. Let's say if the B bit is equals to 0 and we are checking the XOR value within P of 0, so it will be stored in NAB of 0, 0. If the B bit's value is 1 and we are iterating over the XOR values in P of 0, then it will be stored in NAB of 0, 1. and likewise we'll proceed for p of 1 values as well. So this is how we are proceeding with it. And then at last, as I said earlier, we are having this vector ARR, wherein which will be appending these NAB values. After which we are supposed to determine the count. So as indicated, let's take a look at these NAB values. So this NAB array, then it's 0 of 0. We'll be considering P of 0 values, and accordingly within these P of 0 values, we'll be taking only those elements whose B bit is 0. Now NAB of 0, 1. For this, we'll be iterating over P of 0 once again, because your this ith index indicates we are iterating over which value, that is P of 0 or P of 1. So the XOR value stored within P of 0, we'll be iterating over those, and then we'll be storing those XOR values whose B bit is 1. And likewise, we'll proceed for P of 1 values as well. Now, to determine the count, obviously, if you take a look at the XOR operation, so your XOR operation, if both the bits are same, then your answer is 0. If both the bits are different, let's say it's one of them it's 0, then other one is 1, then in that case you will get the maximum value, which is 1. So our aim is to maximize these number of ones within the answer, so as to have maximum XOR value. Now what we'll be doing is, let's write down the same conditions for NAB of 1 comma 0 and 1 comma 1 as well. So we'll be iterating over P of 1 over here, else everything will remain as it is. And likewise. Now let's see how this count variable is getting incremented. So obviously our aim after the XOR operation would be to get maximum number of ones, and to do so we'll be checking those XOR values who are having their B bit set as 0, and those XOR values who are having their B bit set as 1. If we take these two into consideration, then the result that we'll get after doing the XOR operation will be 1 for the B bit, and likewise will continue. So what we'll do, we'll multiply the size of this NAB of 0 0 into the size of this, and correspondingly we'll do the same for them or these two highlighted parts as well, and accordingly we'll add them, and this will repeat for the next iteration as well for all the possible values over this A as indicated over here, because our aim is to get 1 after doing the XOR operation. Now again we'll reinitialize A as an empty vector. Now we'll compare this count with the kth largest beautifulness that we are supposed to get. So this count essentially indicates that if there are possible number of pairs that could be formed, so that the resulting XOR value will be greater than the beautifulness for, or the yth greatest beautifulness or not. That is indicated by this count variable. Now if the count is less than y, it indicates that we don't have sufficient pairs for the bits, so that my value for XOR operation, or my value for the beautifulness that I'll get after doing the complete XOR operation, will not be equals to y. In that case, we'll simply subtract this particular count from y, and we'll be using AB to iterate over this ARR. So it is nothing but a vector which is storing your NAB values after each iteration. Now what this AB indicates, this AB will be your NAB more specifically. Now what this A and B individually indicates is, now as we know, NAB is nothing but an array having two elements within it, right? So the first element within the array will be your A, this one, and the next half of the array, which is NAB, will be your B. Now A of 0 will indicate this is your A. So A of 0 is nothing but this particular vector, and B of 0 is this particular vector. So we'll be checking whether they are empty or not. If they are not empty, then in that case, within A, we'll push back those two pairs, and correspondingly we'll do the same for 1 1 as well, because we don't have sufficient number of pairs so as to get yth greatest beautifulness, and that is the reason we are doing the pairs for 0 0 1 1. Likewise, now let's say if the count is greater than equals to y, then it indicates that we have sufficient number of pairs that could be formed, so that my bracelet that would be formed after taking those bits into consideration will result into yth greatest beautifulness. Hence, we'll go within the else block. Now, within the else block, we'll determine the answer at first. So as indicated, the B bit has to be set as 1, because our aim is after doing the XOR value, we should get 1 for that particular B bit. Likewise, so we'll use the left shift operator. We'll shift 1 towards the left hand side by B number of times, or by B bits, which will indicate that this B bit will be set as 1, or this B bit will be set within the answer, and accordingly after each iteration your answer value is getting updated, or we are doing simply answer equals to answer plus this particular expression which is over here. Now we'll do the same thing. Now we'll be forming up the pairs for which we are having AB, which will be iterating over this ARR. Now again your AB will be simply this NAB array k elements. Now your A indicates the first half of it and B indicates the next half of it. So we'll be checking the values for 0 and 1. Now our aim was to get 1 after doing the XOR of the B bit for those pairs. Hence, we are considering A of 0. Your A of 0 is this pair, that is NAB of 0 0. This pair is your A of 0 and B of 1. So what is B? B is this, and B of 1 is this particular pair. So as indicated within this solution, we are doing the pairs for this and this, because these two pairs will give us the XOR as 1 for this B bit. And likewise we'll be doing for A of 1 and B of 1, that is for these two values as well. And we'll push them within the A vector which is over here, and we'll repeat this particular process from 59 till up to 0. We have already seen the result reason why we are taking these two bounds itself. This is what the answer that we'll get, after which we'll simply output the answer, and let's run the code. It's running perfectly. So before submitting it, let's summarize it up. So what we are doing, initially we are having a vector of vectors which is indicated by this block. Now within this vector of vector corresponding to a particular color, we'll be taking this color -1 as the index, and at that particular value we'll be storing the beauty for that particular bit in the form of a vector. That is, there might be multiple bits having similar color, so we'll be considering the color only once, and accordingly we'll form an array for all possible beauty values which are given within the question. Likewise, then we'll sort it according to the size of the sub vector which is over there, after which we'll be using the meet in the middle approach, for which we'll have two different disjoint subsets, and accordingly we'll be appending the XOR values. If P of 0 is having greater size than that of P of 1, in that case we'll put the XOR for, within P of 1, and if the case is reverse, then in that case we'll put it in P of 0. Likewise we'll continue, after which we'll be iterating from 59 till up to 0. The reason being, the constraint specifies that the maximum value for a particular beauty is 2 to the power 60, and here we are doing the right shift operator which indicates x upon 2 to the power b. Now your 2 to the power b shouldn't exceed 2 to the power 60. Likewise, then we'll be having array wherein which will be or a vector wherein which will be appending this NAB array repeated number of times. Now will be within this NAB array, will be storing the XOR values, or will be segregating those XOR value as per their B bit value. So if your B bit is set, that is B bit is equals to 1, and you are searching for the XOR values within P of 0, then in that case you will store it in NAB of 0 comma 1. If it's P of 0 and your B bit is equals to 0, then it will be stored in NAB of 0 comma 0, and same thing will repeat for NAB of 1 comma 0 and 1 comma 1, which are the XOR values within P of 1. We are simply segregating these XOR values within P of 0 and P of 1 over here. Now we'll be checking the count. Now obviously, after doing XOR, the aim is to maximize the number of 1 bits within the binary term, or within the binary equivalent of your answer. So in order to do that, we know that this particular vector will store all those elements having their b bit equals to 0, and likewise this particular vector will store all those elements or XOR values who have their b bit set as 1. So we'll be taking these two as pairs, because when we'll club them, then in that case your XOR value for that b bit will be equals to 1. Likewise, so hence we are doing the multiplication for the sizes to determine the number of elements within this vector and number of elements within this vector, and accordingly we are incrementing the count. Now we'll be checking the count with y to determine whether we have sufficient number of pairs with us for the bits so as to form the bracelet which has create kth largest beautifulness or not. If it doesn't have it, then we'll simply decrement k by count, and accordingly we'll form the pairs. Now as the count is less than y, so we'll club those members which are having same value for that particular bit. That is, it will result into 0 value after doing the XOR for that particular bit only. And likewise we are appending a of 0 and b of 0, a of 1 and b of 1 in pairs. Else it indicates that the count is greater than equals to y, which indicates that we have sufficient number of pairs of bits that could result into an XOR value with y at largest beautifulness. So we'll determine the answer by simply right shifting 1, so that we'll be setting this b bit as 1 within the answer value, after which obvious thing is we have to club now those member which will give us the XOR value 1 after doing the bitwise XOR for that b bit. So we'll be clubbing a of 0 with b of 1 and b of 0 with a of 1 likewise, and hence we'll get our answer after doing this particular thing in iteration. Now let's submit the code. Yeah, it's getting accepted. I hope you have understood the solution. Thank you for watching.